Hello everyone. In this video I am going to explain uh, the VI characteristics of the Zener diode. Basically I will do the experiment on multisim to evaluate the VI characteristics of a Zener diode. So as you know, this Zener diode works in a reverse bias. So it is a heavily doped it is also PN junction diode. It is a heavily doped PN junction diode. It works in the reverse bias conditions, and in the reverse bias and the VI characteristics are in the reverse bias, the Zener breakdown occurs, and once the breakdown occurs, then voltage remain fixed, but the current through the diode, Zener diode, increases rapidly. So since the voltage is fixed or the constant, therefore this Zener diode can be used as a voltage regulator. So let's see how we can evaluate or experiment the Zener diode to evaluate the VI characteristics. So we'll start it in a multisim. So let's start. So this is your multisim. Okay. So before that, I'd like to just show you the Zener diode. So here, as you see, this is your Zener diode, commercially available Zener diode. This Zener diode in the market you will get in different voltage. That means that different breakdown voltage. Say you can get 2.2 volt Zener diode. That means the breakdown voltage for the Zener diode is 2.2, 4.7, like 5 volt, 5.6, 9 volt, like the different breakdown voltage Zener diode is available. So since it is a PN diode, so as you can see at the top, one side at the top there is a black stripe. So this black stripe indicates the N side of the diode, N side of the diode, and the remaining the other side is the P side of the diode. So N side, that is your cathode, or the P side, that is your anode. Okay, so this is your N side, this black stripe. Wherever you see the black stripe in the real diode, so that side is the cathode or the N type, and the other part is the P side. So this is the symbol of the Zener diode. So it looks like a normal PN diode only thing is that this stripe is slightly like this. It is just to indicate the Z, looks like Z. So Zener diode. Okay, this is your anode, this is side your cathode, this side is your P type, this side is your N type. Okay, so now I'll go to the multisim. So in the multisim, as in my previous video I have shown, the simulation can be done using here the multisim simulation, like analysis and simulation, from where we can do the interactive simulation. All this different analysis is done. So interactive simulation means without using this multisim, we'll manually will operate, and here, since it is a DC by a Zener diode operates in the DC bias condition, so what we can see here is the DC sweep. So what we use this DC sweep, so without varying the voltage, it will do itself the analysis. So we'll start with that. Okay, so for that what we need is we need a Zener diode. So this place for the diode. Okay, so from here you just click Zener. Okay, so there are many different varieties of the Zener diodes are available. Okay, so these are the different Zener diode with different voltages. Okay, sorry, these are the different Zener diode with different voltages. So let me take one very simple Zener diode. So let me take this 4.7 volt Zener diode. Okay, so this is the Shiba made 4.7 volt Zener diode. Okay, so let us take this. Okay, Zener diode. So next I need one resistor, so that can be used as a current limiting resistor. Otherwise the Zener diode might start malfunctioning, so I mean it might get damaged because of the high current flow from the source. So let me take one current limiting resistor. So this is your found in a basic. So under this basic, this is your resistor. So let me take 1k resistor. Okay, so 1k resistor. Then what next is we need is source. So DC power source, DC power source, and we need one ground. Okay, sorry, we need an ground, so that the ground is in source. Okay, this ground. Okay, for the timing these 4 components are required. Okay, so let me connect it. I have connected here this, and since it is reverse bias, Zener diode has to be connected to reverse bias, so this N side has to be connected with the positive terminal of the battery. So this is your N side connected with the positive terminal of the battery, and the negative side is connected with the positive, P side of the Zener diode, and ground is connected here. So that's all. So now let me save it. Okay, now go to the simulation, analysis and simulation, go to the DC sweep. So source voltage is V1. Yes, this is your V1 source voltage. Then start value I'll put 0 and stop value say 12, and with an increment of 0.5 I will analyze 0, 0.5, 1, 1.5, 2.5, sorry 2, 2.5, 3, 3.54, like that it will go on. Then in the output, the current, so current, whatever be the current passing through the R1, that will be, because it is in series, so that will be also current through the Zener diode. So I will take this IR1, this is already taken, IR1. Okay, so save, then just run it. This is your run. Now see, this is the characteristics. Now thing is that in Zener diode, since it works in the reverse bias, so obviously while you analyze the applied voltage, you see this side is positive and this side is negative. Okay, so current is actually flowing through this, but here it is showing this way. But in normally, or in the actual plot, while you make it in the graph paper experimentally, then it will come into the third quadrant. That means applied voltage is, because it is negative bias or the reverse bias, so x-axis is in the negative side, and also current passing through the negative in the opposite direction, so therefore it is in the negative y-axis. So therefore actually this you just imagine like a negative x-axis, this you just imagine like a negative y-axis. Okay, so now see, somewhere, since this diode is of 4.7, somewhere here at the 4.7 it gets breakdown. So till this you see, these are the your, okay, sorry, so till this the current is 0, and somewhere here, since it is 4, 6, so somewhere it is 5. Okay, somewhere it is 5, and 4.7 means somewhere here, so it gets breakdown here, and from that it current increases. Okay, current increases. But ideally it should be like this way, straight, but practically it is linearly increasing, so here it gets breakdown. So this is very practical diode is used, that's why. Okay, so this is the reverse bias characteristics of the VI characteristics of the Zener diode. Okay, now while we do this in actual physical laboratory, how will you do this? Okay, I'll just show you that. Taking the reading one by one. So for that, let me take one Excel sheet where I'll record the values. Okay, where I'll record the values and little modify the circuit. Here I can take one potentiometer to vary the voltage, or since it is multi-sim, we can do like this way. This value from 12 I'll make it say 0, then 1, then 2, like that also we can do. So that I think that would be better, because sliding the potentiometer in the multi-sim is very difficult, very sensitive. Okay, so what I'll do is I'll connect a multimeter. So this is a multimeter, and let me take one more multimeter, one for the voltmeter, one for the ammeter. So here I'll put the ammeter. Okay, here I'll put the ammeter. Okay. And here I'll put the voltmeter. Okay, voltmeter here, across the diode. Okay, so always the voltmeter is in parallel, and ammeter is in series. Okay, Now if we double click this monitor will open for this. Now it is, you see, this is V for it is working as a voltmeter. So let me put it as emitter. Then this is your voltmeter. Both are DC. Okay, you can set the value here. Okay, and resistance, voltmeter resistance and all. You can these things. Okay, in whatever be the values are now there, it's okay, ideal. So now just save it and let me open this Excel sheet where I'll put the values. Okay, so here's a serial number, then VS is your applied voltage. Okay, applied voltage, then current, so let me put it as ID, current passing through these things, and voltage across the diode, so let me put it as diode. Okay, so this is voltage across the diode. Okay, this is your current through the diode, ID, and this is voltage across the diode. So let some few readings. Okay, so the voltage say like I'll put it as 0, 0.5, then 1, like that we'll put. So up till 12 volt will get. Okay, so let me take 25 readings. Okay, now let us start. Okay, so now it's a 0 volt. So while I run it, okay, before that I'll put this analysis as interactive simulation. Okay, now run it. So now you see applied voltage is 0, current passing through the emitter, the diode is 0. This is your current, this is your voltage across the diode is also 0. So let me put it as 0 ampere, 0 volt. So let me put it as volt. Okay, and here whatever be the unit is coming up, we will take it. Okay, now let me change it to 0.5. So 0.5. Okay, now run it. So when it is 0.5, it is 1.049 nano ampere. So current is 1.049 nano ampere, and the voltage is your 499.999 millivolt, and this let us consider it to be 500 millivolt. So 500 millivolt means 0.5 volt. Okay, so now let me change it to 1 volt. Okay, then run it. So now the current is 2.121 nano ampere, and the voltage is 999 millivolt, that is almost 1000 millivolt, that is so let us consider it as 1 volt. Okay, 1 volt. Okay, then so let me put it as let me put it as 1.5 volt. 1.5 volt. So when it is 1.5 volt, the value here is 3.686 ampere, and the voltage is 1.5 volt. See, till the breakdown it will be almost same as that of the applied voltage. Now I am making it 2 volt. Okay, 2 volt. So it will be your 11.036 nanoampere. So that means it is almost negligible current. That means ideally you can consider it to be 0. So here it is 2 volt. Then further I'll make it 2.5. Okay, so then it is 88.685 nanoampere, and the voltage is 2.5 volt. 2.5 volt. Then I'll make it 3 volt. Okay, so if it is 3 volt, then 1.018 microampere. Current is slightly increasing. So the voltage is 2.999 volt. So it is 3 volt. Okay, 3 volt. Then I'll make it 3.5. So when it is 3.5, it is 3.488, almost 3.5. So 11.697 microampere. 11.697 microampere, and it is 3.5 volt. Then I'll make it 4 volt. So make it 4 volt. 94.255 microampere, and the voltage is 3.969. So okay, let me put it as 3.06906 volt. Then I'll make it 4.5. So it is 338.524 microampere, and the voltage is 4.161. See, 4.5. so it is less now, and slowly if I make it say 5 volt, then it will not cross 4.7 volt. Okay, so 4.305 volts. So the current is 694.735, and it is 4.305. So this current is in microampere. Okay, then let me put 5.5 volt. So in the 5.5, you see voltage across the diode is not increasing much, so it never crossed this value 4.7. so it is 1.102 microampere. Sorry, now it comes to a milliampere. Okay, now it comes to a milliampere, and the voltage is 4.398. Then I'll make it 6 volt. Okay, 6 volt. So it is 1.536 milliampere, and the voltage is 4.464. You see, although it is 6 volt, it does not cross the 4.7 volt. Okay, so now I'll make it 6.5. So so it is 1.985 milliampere. Current is increasing. 1.985 milliampere, and the voltage is 4.515. Then I'll make it 7 volt. Okay, so 7 volt, it is current is increasing 2.443 milliampere, and here it is 4.557. Then I'll make it 7.5. So in 7.5 it is 2.908 milliampere, and the current voltage is 4.592. So you see it is almost fixed at 4.5 or 4.6. okay, almost from this point. While you apply, you see 4.5 volt, 4.5, since it is 4.7 diode, 4.7 volt diode, so now almost fixed, you see. Now make it 8 volt. So 3.378 milliampere, current is increasing, but the voltage is still 4.622. Then make it 8.5. okay, so we make 8.5, it is 3.852 milliampere. Then the current voltage is 4.648. okay, then make it 9 volt. So it is 4.329 milliampere. Here also this milliampere, and then voltage is 4.671. Then it is 9.5. It is 4.808 milliampere, and voltage is 4.692. Then make it 10 volt. So now 5.289 milliampere current, and the voltage is 4.711, slightly more than, because the voltage is increasing much, so 4.711. okay, slightly more than 4.7. So next I'll put 10.5. then it is 5.771 milliampere. Then it is 4.729. Then I'll make it 11. okay, then it is 6.255 milliampere, and here it is 4.745. I'll make it 11.5, and then it is 6.74 milliampere, and the voltage is 4.76. Then 12 volt. So in the 12 volt it is 7.226 milliampere, and it is 4.774. So let me put few more readings. So let it be 13 volt. Oh no, it cannot go beyond 13 volt, because this battery itself is maximum of 13 volt. 12 volt. okay, so this much is sufficient. If you look at these values, till 4.8 the voltage is increasing sharply, as it is given voltage. Current is very low, nanoampere than microampere, but you see at after 4.5, because this Zener diode is of 4.7 volt, so at 5 volt it increases sharply, and then onwards voltage, although there is a slight change in the voltage, but very minimal change, I mean very less. So I can ideally you can consider it to be constant, fixed. Practically there will be slightly increase, slightly, say 0.001, 0.002, like that increasing, but the current increasing sharply, you see. Okay, now we'll plot it. For plotting, what I'll do is I'll just change this nanoampere to like this, more scientific notation, E minus 09. Okay, then this is also E minus 09, then this is also E minus 09. This means 10 to the power minus 9 nanoampere. So this is also E minus 09, E minus 09. Now this is microampere, so E minus 06. This is E minus 06, E minus 06, E minus 06, minus 06. Now it is milliampere, so E minus 03. Okay. Okay, so that way it will go on. Okay, so now we'll our values are ready. So now we'll plot it in XY plot. In x-axis the Vs and the y-axis the current ID. So just select it, go to the insert, scatter plot. You can take any one of that. Let me put it as scatter plot. So this is your XY plot in Excel. So you see up till 4, as you see, for till 4 it is almost 0, 0.94, I mean 94.3 nanoampere. Okay, so beyond that 4.5 it increases, so it slowly increases. Somewhere here 4.7 it gets breakdown and it increases sharply. Okay, it increases sharply. So this is the VI characteristics. Again I am telling you that this is in the third quadrant, but here we are just showing the positive voltage, positive current. That means actually it is in the reverse bias, so therefore negative, negative, and it is also in the reverse direction, so it will be negative. Okay, that also you can just see if I put the value negative. Okay, just edit it. Actually how it will be look like. Likewise, if I put the negative values, then we will see the graph in the negative direction. Okay, so all the values I made it negative. Thing is that while you experiment it physically, you won't get the negative voltage or negative current. It will be just the polarity is reversed, so you will get the positive only. But while you draw the graph in the graph paper, always use the third quadrant to plot this. Okay, because it is reverse bias. Now I will just plot it. So insert, scatter plot. So you see now so this way actually it looks like. So you see till 4.7 there is no breakdown. Ideally it should be like this, straight way it will go down, but it is linearly going down. Okay, So now the same thing I'll just show you in the how we can do it in MATLAB. So this is in MATLAB. In MATLAB what I'll do is this is your MATLAB environment. In MATLAB I'll just show you quickly how to plot the values. Okay, so I'll just create a blank variable, say x, the square bracket, it will make a blank variable. Okay, so now this in this workspace, this is what is called MATLAB workspace. This is your command window and this is the current folder window. And now if I double click on this, it will create open it in a variable editor window. So this variable editor window is something like your Excel. So now just I'll put the values in Excel. These values just simply copy and paste. Okay, just copy and paste it here. Just copy and paste. Yes. So these are the x values. Then similarly I'll make one y variable. So now just click on the y. So I'll just put the values here, the y values. Okay, just copy and paste. Okay, so these are the y values. Now thing is that this is in the column form, so while plotting in MATLAB it should be in the row. So MATLAB everything actually is in terms of the vector, that is matrix. So MATLAB for matrix laboratory. Now if we type x here in the command window, you see all is in column. So what I'll make, x is equal to x prime, it will make the x vector transpose, that means the columns to the row. So x prime, it will make it transpose, that means row column becomes row. So now it is in the row. So if you now double click on the x, now see it is in the row. Okay, similarly I'll make y prime. Okay, so then y also becomes here this row vector. Now simply just plot plot within bracket x comma y. So it will plot the graph. So this is a graph. Okay, as you see, this is current is increasing up till this 0.4. So let me put grid. Okay, just plot grid, just comma grid. Okay, so this is the plot. So this is -4, somewhere here it is 4.7. Okay, it gets breakdown shortly. Okay, so that's all. This is your Zener Diode VI characteristics. So exactly this circuit you will make in the lab, I mean physical lab. So you just take a variable power source. If you have a constant power source, then connect a potentiometer across it and rotate the potentiometer to vary the voltage across this. And this emitter to measure the current passing through the diode in series, and this is the voltmeter to measure the voltage across the diode, which is in parallel. Okay, so that's all. Oh, it's still running. Okay, let me close it. Okay, thank you very much.